So I just want to say a couple things first. So first thing is I posted a review from a couple of years ago. Actually, not last year. So the one last year, no one asked me anything just about, for some reason. I don't know why, but there was like 2 simple questions, and that was it. And the year before that, I didn't have all the notes for it. I don't know where they went. So I had to go back 3 years. But anyhow, the 3-year one, 3 years ago, was pretty good. They asked a lot of questions. And it's the same topics. So I put that up there already. And the other thing, there was a typo on one of the quiz questions, number 6. If you go look at I switched 2 of the batteries by accident. I didn't see it until I was doing way after I posted it. So I'm giving everyone just 10.5 points for quiz 6, right? Added up to that. But you could look at, if you switch the batteries, then you get the right answer, and you should look to see how you do with the battery switch. But that was a problem with the quiz. And that's all I wanted to say. So everything's posted, right? All your quizzes are posted, the homeworks are posted, your equation sheet's posted, obviously all the lectures are posted, the PowerPoint's posted, and the review from 3 years ago is posted. But then there's this review, right? Which will also be posted. What was that?
I said review from 3 years ago.
It says, it's with the review sessions, and I said,
yeah.
I said test 2 review from previous semester or whatever. Anyhow, so what do you want to do? I assume that you want a little bit, maybe another question with the loops, since it's going to be on the test, right? And then we can go from there after the loops question. So I anticipated that, and I made a loop. I made this up ahead of time because I wanted to make sure that the numbers came out okay. So this is your circuit. I'll give you a second to copy it down, and then I'll ask you something related to the circuit.
Oh, yeah, I'm not copying it down.
We should post it the night before so we can print it and then fill it in.
Yeah, that's true. But it's kind of
Time-consuming?
Yeah, to do that. Although it is a good idea. Oh, sorry. 120.
Oh.
That's better.
Huge battery.
Yeah, they're kind of big. It's not complicated.
Just a big number. Doesn't mean that it's
You're running 4 batteries.
Yeah, the numbers really don't matter that much. Yeah.
I just want to make sure all the Kershaw stuff is going to be on the exam.
Oh, yeah. Yeah. I'm just going to pause the video while you copy it down. Okay, so the question is, I'm not going to write the whole thing down, but it's a standard setup, right? So using the 45-volt battery, which is the battery that's circled, clearly, you draw the initial current, and then call the currents the standard things. In other words, the current coming out of the 45-volt battery is I. The one going through the 25-ohm battery is I1. Sorry, resistor, 25-ohm resistor is I1. And the one going through the 2-ohm resistor as I2. And using the loop on the left and the loop on the right, write down 3 equations which can be used to find the 3 unknown currents. Once again, on the test, you're going to have a similar circuit. It's not the same circuit. You have batteries in different places, maybe flipped around, so the plus minus is flipped. But it's the same basic circuit, right? So you're going to have to do this for part A of one of the written questions. So the simplified versions, try to simplify them too, right? Okay. So does anyone want to tell me the loop equations, or do you want to just do it? Okay. All right, so the first thing you need to do is draw the currents correctly, right? Which I hope everyone knows, so I'm going to go through it maybe a little quick. But you have the main current I coming out of the battery. You have I going through that resistor. You have I1 going down the middle, because it splits up at this junction, right, into 2 different currents. So that's I1. This is I2. I2 goes through everything here. And then it goes through that resistor. And so then, so some people don't know this for the test. After this junction, right, what is this current? I. Okay, because some people write I1 or I2, right? But it's I, right? It merges back into I. Okay, so that's the first thing you're gonna do. Then you gotta draw the two loops, like what what loops you're using. So we're using the loop on the left and the loop on the right. And like I say, we always go around the same way. You could randomly go around the other way if you wanted to, but it's the same equation, so just always go around that way. And then, you don't have to do this either, but I like to do it. It's just draw an X, so just so you know like where you start, where you end, so you go through everything. Okay, so the first thing we see is this, for loop 1 here, right, the loop on the left. The first thing we see is this 45-volt battery. So we go from negative to positive across it. So is that a gain or a loss of voltage?
Gain.
Gain. So you write down plus 45 for that one. The next thing I see is this 5-ohm resistor. I go with the current through this 5-ohm resistor. So do I gain or lose voltage? Lose. How much do I lose exactly? Times I, right?
Times I.
So you write down minus 5 ohms times I. And then I have to go down the middle. So the next thing I see when I go down the middle, in fact, the only thing in the middle is this 25-ohm resistor. So I'm going with the current through that resistor. So is that a gain or loss? Loss of what? Right, I1 times 25. So you write down minus I1 times 25 ohms. And then I have to go back this way to get to this X. So I'm going to the left along the bottom. Anyhow, the next thing I see is this 120-volt battery. So I'm going from the positive end to the negative end. Right, so it's minus 120. And then the next thing I see is this 15-ohm resistor. I'm going with the current through that 50. Right. So when I write all that down, probably not going to remember the whole thing. It's plus 45, right? And it's minus I. What's that resistor up there? 5 ohms, okay. And then minus I1 times 15? 25, sorry. I don't know why I thought it was 15. 15's right there, right? Okay, so anyhow, minus 120 minus I times 15 is equal to 0. And then you gotta, try to simplify it. You can take out your calculator if you want, but 45 minus 120 is negative 75, right? So you have minus 75, and then you have minus I times 5 ohms minus I times 15 ohms gives you what?
20.
Yep.
So minus I.
Yep. And then you just have the one thing with I1, right? So you don't have to simplify it. All right, so that's the simplified version of loop 1's equation. Okay, so let's do loop 2. Okay, so loop 2, I'm starting at this X, going around clockwise. Anyhow, so the first thing I see is this 10-volt battery. So you go from the negative to the positive across it. So is that a gain or a loss? Gain. Right, so you're down plus 10 volts. The next thing I see is this 2-ohm resistor. I'm going with the current through that 2-ohm resistor. So do I gain or lose voltage? Lose. Right, minus I2 times 2 ohms. So then you write minus I2 times 2 ohms. The next thing I see is this battery, 360-volt battery. So I go from plus to minus across it. So do I lose or gain? Right, I lose. So you write that minus 360. The next thing I see is this 13-ohm resistor.
Yep.
And I'm going with the current through that one. So do I gain or lose? Lose. Yeah, minus 13 times I2. And then to get back to the X, I have to go up through the middle, which some people don't understand why you're going against the current, because you have to go up to get back to this X, right? So when you're going up, you're going against the current. And is that a gain or a loss?
I1 times
Gain. Gain when you're going against the current, right? So it's plus I1 times 25, right?
Yes.
You're going against the current to get back to the X. You're going up through the middle to get back to the X, so it's against the current. Okay, so let me write this down. I'm never going to remember this. I wrote it down in a different way. Okay, so it's 10 volts minus I2 times 2, right? I'm writing kind of fast. It's a little bit messy. Minus 360 minus I2 times 13, right? And then plus I1 times 25, right? Equals 0. And then you just got to simplify it. So this is negative 360 plus 10 is minus 350. And then minus I2 times 2 ohms minus I2 times 13 ohms is minus I2 times 15 ohms. And then you just have the one thing with the I1 again. So that's the simplified version of loop 2. I was just double checking, make sure everything looks okay. Yes, it does. Okay. So then that's 2, right? You also need the third equation, which some people forget quite often, actually. It's not just a few people. Usually a chunk of the class doesn't write it down. So what's the third equation you need? Right, so do not forget this, right, on the test. It's the same equation, right? It's even on your equation sheet, I think. I'm not quite sure, but anyhow, it's the same equation all the time, right? So the loop equations are different, but the junction equation is always the same, so you just need to write it down. And you think it's, sort of a minor thing, but it really isn't. I mean, you need 3 equations to find the 3 currents. So anyhow, you need to write all 3. Okay, so those are the 3 equations. Okay, so I guess that was part A. I didn't write part A, but this is part B. Okay, so when the correct equations in A are solved correctly, I guess, you could write the wrong equation down or write the right ones down and then solve them incorrectly. But if they're solved correctly, I is minus 10 amps, and I1 is plus 5 amps. So they work out to be nice numbers, actually. That's why the voltages are so high, to make the currents work out. Anyhow, so the question is, what's the power output of each battery? Okay, so try to figure that out. Let's see. Okay, so let me just see if anyone has correct answers for a couple batteries, random batteries. Does anyone have the power output for, say, the 45-volt battery?
-450.
Okay. Yeah, that sounds pretty good. Okay, what about the, I'm going to pick 2, and then I'll just do them all. What about the 360-volt battery?
5400.
Yeah, okay, that's good. Okay, so let's see how you do this, right? So the first thing you should, I'm going to move this circuit down. The first thing you should do before you correct the currents, which is what you should do, it's a step that you should do, is find the unknown current, right, that you don't know. I'm always going to give you 2. You have to find the third one. So how do you find the third current, which is I2?
Your junction equation.
Right, you solve the junction equation. When you do that, it's I minus I1. Now you do not change any currents at this point. Whatever currents I gave you, you plug them in here, right? So for instance, I is minus 10. What is going on? My computer always works weird in this room for some reason. Which is good, because it works fine in the other rooms where I teach. That's where I really need it to work. Anyhow, so you get minus 15 amps, right? That's the current for I2. So I2 and I are both negative, but I1 is positive. So what that means is that I1 and I2, sorry, I and I2, not I1, I and I2, are in the wrong direction. So you got to switch them, but their amounts are 15 amps and 10 amps, right? They're just in the wrong direction. So that's the second step. You don't switch the currents right before you find all the currents, because it'll be sort of confusing. So what that means is that I is in the opposite direction as how I drew it. Totally missed that. All right. It's kind of a pain that I drew so many arrows. All right, so I goes through there, and then it doesn't matter for the resistors, but I'm just switching everything so it's consistent. All right, so that's I.
On the exam, do we have to redraw it, or can we just correct the original? Or do you want to see 2 different ones?
No, I mean, we're looking for the correct answers.
Okay. So
I mean, the work to get the correct answers, but I mean, if you can see how the correct circuit looks in your head, then you don't have to switch it, right? But the negative and positives are important, right? If you get the wrong
Yeah.
signs, that's technically not, right? Well, not all wrong, but you lose points, right? Yeah, yeah. Well, I mean, really, it should be, yeah, oh, something like that, yeah. Okay, so this is 10 amps, right? But it's going in that
Did you get it
direction.
wrong?
But see, some people have it completely backwards on the test and do everything wrong, every single sign wrong. So hopefully, if you miss a sign, it's just one sign and not all of them. Anyhow,
Correct it with a different color.
so I2 goes like this, and I2 is like this, and I2 is, what was it? What was I2? 15 amps, right?
Yeah.
And I1 is 5 amps. Okay, so now the circuit's corrected. That's a very important thing to do because that tells you the power output of the batteries, whether they're positive or negative, that is. So for the negative, for the 45 volt battery, right, the actual current's coming out the negative end, right?
Yeah.
So this one's negative. I just circle. It's easy. Maybe it might help you if you circle what it comes out of so you can just see what are positive or negative, easily. It helps me sometimes. Yeah.
Why is it coming from the negative end?
Why is the current coming out the negative end, or why is it negative power?
Why is it coming out from the negative?
Because there's other batteries in the circuit, right? There's 4 batteries, right? Okay, so then for the 120 volt one, the current of I is coming out the positive end, right? So that's positive. And then for the 360 volt battery, the current 2 is coming out the positive end. So that's positive. And for the 10 volt one over here, it's coming out the negative end. So you have 2 negatives and 2 positives, right? They're not all positive. And then you need the right currents too, that's the other thing. So for the 45 volt battery, it's minus 45 times 10 amps. So these are kind of easy to do almost in your head, right? It's negative 450 watts, right, for the 45 volt battery. And then for the 120 volt battery, it's plus 120 times the current coming out of it, which is 10 amps. So you get plus 1200 watts, right? And then for this one, the 360, it's also positive times the current coming out of it. So that's 15 amps. That's a little bit harder to do in your head, but it's 5400, right? And the last one is a 10 volt battery with 15 amps coming out of it, right? So it's minus 10 times 15. And that's easy to do in your head, right? So it's minus 150. So that's the question I asked. But then if you add all these up, you get the total power output of the batteries, right? If you just add those things. And that adds to be 6,000, I'm pretty sure, right? So if you add those four numbers up, the total power is 6,000. Now, even if I don't ask this, it's good to figure out because you can use it to check your work later on, right? So that's the total of all the batteries at 6,000 watts. So another question I could ask is, what's the power dissipated by each resistor? And what I'm saying is, if you find the power from each resistor, or dissipated, and you add them up, what do you think it should equal if you did everything correct? It should be equal to 6,000. So it's another good way to check your answer, right? If you get 2 different numbers, it definitely means you're doing something wrong, right? So see if you can figure that out. Okay, I'm not going to do every resistor, but let me just pick a random resistor and see if anyone has an answer. Let me pick the 5 ohm. Does anyone know the power dissipated by the 5 ohm resistor?
500.
Hold on. Yes. Okay, what about the 2 ohm resistor? Yes. Okay. So to do the power dissipated by resistors, all you need to do is figure out the current going through them, which is I for the 5 ohm and the 15 ohm, Square that and multiply by the resistance. For the 25 ohm, it's I1 squared times 25, and then for the 2 ohm and the 13 ohm one, you have I2 going through them, so it's I2 squared times 13 ohms and 2 ohms. That's it. And then if you add those up, you should get the power of the battery, right? If you did everything correct. Anyhow, so if the 5 ohm had I going through it, right? The current I, which was, what is I? 10. Okay. So it's 10 amps squared times 5 ohms, so that's 500 watts. Let's see, the 15 ohm, right? That's the other one that had I going through it. By the way, so all right, I'll just write it out. That'll show you something after I'm done writing. So 15 ohms is how many times 3? How many times 5? Sorry. 3 is what I was trying to. So if you do 500 times 3, that just gives you, that one. Or you can just do this. 15 times 100 is 1500, right? Either way, it's the same thing. But it's good to think in proportions sometimes, right? Okay. Now, the one in the middle had I1 going through it, right? The 25 ohm one?
Yeah.
So that I1.
It was 5.
Yeah. So it's 25 times 25, which is 25 squared, which is 625, right? And then the last two had I2 going through them, so that was a 2 ohm one. I'm writing 2, but anyhow, you get the idea. Should maybe write 2 ohms, but it doesn't matter as long as you label them so you know which one's which. Okay, so this is I2, which was 15, right? So it's 15 squared times 2. So it's 35 times 15, which is 450, right? And the last one also has I2 going through it, which was 13. It's a little bit hard to do proportions with 2 and 13, but it's, what, 6.5 times bigger? 6 is 12, right? So it's 6.5. If you multiply this by 6.5, you get the other one, right?
Can't do it. When it's easy proportion.
Yeah, I mean, it's a little bit harder to do proportions, but anyhow, if you multiply this by 6.5, you should get 2925. Anyhow, and you know that you did things right if you add these things up and you get 6,000, which you do. I mean, I'm not going to do it, but
I checked.
yeah. So, but it's a good way to check, because if you get 2 different numbers, it definitely means something's wrong somewhere, right? So you should do it so you get full credit for one. I mean, no one should lose a huge amount of points in this problem. I mean, I see maybe getting a small thing wrong here and there, but not knowing how to do it completely, no one should be in that position, right? Okay.
I hope not.
Yeah. There'll be a few. I know it, because every semester I warn people, and every semester there's a few that have no idea how to do these problems.
Is that what you always tell people that this one's going to be on the exam?
Yeah. I tell them it's going to be an exam. I say, make sure you know how to do it. And there's a chunk of people that don't know how to do it. So, I don't know, but that's how it works out. Okay, so what other questions do you have? It's good that we did this one. So there's a bunch of Kirchhoff loop rule examples, right? We did some in the homework, some in the notes, some in the PowerPoint, yesterday in the review session, another one in the other review session. So there's a bunch of examples, right?
Yeah.
You should be able to figure it out by now, hopefully. Okay, so what other questions do you guys have?
Back in quiz 3 when you had delta KE, find the kinetic energy, could we do something like that?
Yeah, we could do something like that.
We weren't expecting that. You were
No.
not expecting that.
No, actually, I was looking through the review session from 3 years ago,
Oh, I didn't look at it.
and there was something similar to that someone asked me, but I don't remember what the question was. Okay, so let's do something in reverse. So you have all right, all right, suppose a uniform field is directed in, so I'll help you out. I mean, you should be able to figure it out without, just by the context of the problem, but it's positive y or minus y direction. We don't know which way it's going. Uniform electric field, obviously. At this point, you know, as of this test, you only know electric fields, although we're learning about magnetic fields. Okay, so it's directed in the positive y or negative y direction. Okay, so as, I don't even know how this is going to work out, but we'll see. Okay, so as a charge of, say, minus 2 microcoulombs moves, let's say, 0.4 meters in the positive y direction, its speed changes. I have no idea how this is going to work out, by the way, but we'll see. From 5 meters per second to 20 meters per second, due to only the electric force. In other words, we're going to ignore gravity and everything else. Okay. Okay, so I have to give you the mass of the charge, too. I always think about, I'm just trying to type and I forget things sometimes. The mass of the charge is 0.2 kilograms. Okay, so given this information, this is a tiny bit of a tricky question, but see if you can figure it out. All right, how much does the electric potential energy of the charge change? All right, the better way to say that is, what is the change in electric potential energy? Okay, that's much better. Okay, so try to figure that out, see if you can figure it out. Okay, so does anyone want to say an answer first before I?
I'll give you the magnitude.
Okay.
3 times 10 to the negative 5. But that's completely wrong. It's really completely wrong.
Yeah, it's a little bit off.
A little.
A little bit off.
A little. Half.
Anyone else have an answer first? No? Okay. Okay, so what we know is, well, what do we know? We know how fast the charge is moving at 2 different points. We know the mass of the charge. We know the charge itself and how far it's gone. So what are the relevant things here? Okay, so the change in electric potential energy depends on the charge, first of all. But it also depends on the change in potential, which we know nothing about right now. So you cannot do it using that equation because we don't know the delta V. However, there's something else we can figure out if we know the mass and the initial and final speed. Does anyone know what else we can figure out if we know the mass and the initial and final speed? All right, we can find the change in kinetic energy. That's one thing we can find. So what is the change in kinetic energy? It's 1/2 the mass times the final speed squared minus 1/2 the mass times the initial speed squared. And, you know, so we can just plug this in and get some number for the delta T. So it's 1/2 times, I don't know why this thing. Yeah, I mean, it never does this in class. It never does this any other point except this room, which is weird. So anyhow, and then you just, it's the same thing, but you put 5 here instead of 20, right? So, you know, it's the final minus the initial. So it started at 5 and then it ends up at 20. So it's 20 is the final and then the initial is 5. So you just plug these numbers into your calculator and you get 37.5, right? Positive 37.5 because VF is bigger than VI, right? So this number is bigger than that, so you get a positive answer for your delta KE. Remember, KE cannot be negative. This is like from test 1, but delta KE could be negative, right? It could be speeding up or slowing down, right? If it's slowing down, then delta KE is negative. Now, we're going to use this to find the change in electric potential energy, because one way you can write down conservation of energy, right, is that delta E, you can write it down. We did this in the notes. And I'm pretty sure one of the quiz problems was like this. The change of energy is the change in kinetic plus the change in electric potential. And that's the only things you're factoring in. And this is equal to 0 because there is no non-conservative work, right? I mean, you're only including the electric force, right? I mean, all these problems, we've never even seen a problem when there's no non-conservative work, and you won't see it on the test either, right? So it's just, no non-conservative work. So that means that the delta EP is just the negative of this. I'm pretty sure this was a quiz question on quiz 3.
Yeah.
So it's the same thing here. So it's just the negative of the delta KE, right? Delta EP is negative delta KE. So that means that delta EP is minus 35.05. Negative 37.50 joules, right? Okay, but the important thing is, now that we know this, we can ask questions related to this. For instance, you can ask, now this is easy if you figure this part out. This is the hardest part. But still, what's the change in electric potential for the charge? So then, hint is using this, you can find the delta V, which should be fairly straightforward, hopefully. Okay. Does anyone have an answer for the delta V?
1.875
Yep. Yep, it's because delta EP is the charge times delta V. So delta V, which is what I'm asking, is the delta EPE divided by the charge, but there's no absolute values, right? So in any of these equations, so the delta EP can be plus or minus. Obviously, it's negative here. And then the Q can be plus or minus, obviously, and it's negative. So it's negative 2 times 10 to the minus 6th. Coulombs, right? And when you do that, you get the delta V is a big number, but it's positive. 1.88 or 1.875, say, times 10 to the 7. Well, but you can get big answers for V's, or delta V's for charges. It's not a big deal. It's a big number. Okay. So then using this, and I'll explain a concept related to this after we're done answering the next question. But the next part is, what is the amount and direction of the electric field? All right, so it's positive Y or negative Y. I already told you that. But which one is it? Is it positive Y or negative Y? And how much is it, right? All right, does anyone have an answer first? All right, does anyone have an answer for the amount of the field, or the magnitude of the field?
4.7
Yeah.
Positive. I'm saying it's positive. I don't know if it's positive.
Okay, I actually have to go up and look at it again. But let's go through the magnitude first, then we get to the direction in a second. So the magnitude, so first of all, the change in potential is equal to plus or minus ED. So it's either plus ED or minus ED, depending on whether you're going with the field or you're going against the field. But obviously here it's positive because we're getting a positive answer, right? For the delta V is positive, right? So it's positive ED, right? Getting negative ED because the delta V is a negative, right? So to find the amount of the field, it's just the change in potential divided by the distance that the charge went. So this is the change in potential. We got it from the change in electric potential energy. And if you divide that by how far the charge moved, which is given in the beginning to be 0.4 meters, this is the amount to the field. Once again, it's a pretty big number, but it's like 4.69, something like that, times 10 to the 7th. And you can actually use volts per meter here. Remember, volts per meter is the same unit as newtons per coulomb. Okay, so that's the field. Now, we have to figure... Okay. Yeah, so we have to figure out what's going on here. So when is the delta V positive ED as opposed to minus ED, right? So what's the general idea?
The charge is going against delta V is going to be positive.
Positive, right? So if the charge is moving against the field, another way to think about it is towards a positive charge, then the delta V is going to be plus ED. If the charge is moving in the same direction as the field, it's minus ED, or another way to think about that, it's towards a negative charge. So this charge is moving in the positive y direction, right? To get a delta V, positive delta V, that means the electric field is in the negative y direction, correct?
Mm-hmm.
All right. I'll write that down. Then I'll sketch it out because it may be easier to see with the sketch. For the change in potential to be a positive number, the charge must be moving against the field. Okay, so since the charge is moving in the positive y direction, right? Oops, the field is negative y. Yeah, so you could say that the you could just write it as electric field vector, right? So it'd be like plus, negative y, sorry. Negative y hat, right? That'd be the way to say it. It's sometimes easier to sketch it out. So if you suppose the uniform field is created by a parallel plate capacitor or by a single sheet, but it's easier to visualize with a parallel plate capacitor. So suppose this is a parallel plate capacitor and this is the charge, right, in capacitor. We know it's going in the positive y direction. This negative charge, right? So we know it's going positive y. Oh, jeez. I'm just trying to draw an arrow, but this thing isn't letting me draw it today. Anyhow, it's going, up there. This is 0.4 meters, right? This is how it's moving, not the velocity, right? That's how far it's going. So it's speeding up, right? So that means this has to be a positive charge, and this has to be the negative charge, right? And if that's the positive charge and that's the negative charge, then that means the field,
Goes from positive to negative.
right, goes from positive to negative. So it's like this. Yeah, so sometimes if you sketch things out, it makes sense. When you think of uniform fields, you can think of capacitors because they produce uniform fields. And it helps things too. And this is why the delta EP was, well, we can look at all this stuff, right? The delta EP was negative, right? Why is it negative? It's because the charge is going in the direction that it wants to go, right? It wants to go towards the positive charge, so you should have a delta EP as negative. Why is the delta V positive? From this point of view, because you're going closer to a positive charge, you're going against the field, right? So it all makes sense when you sketch it out, right? And that's how it works. Okay, that was a good question. Any other questions? So something you should sort of understand too is like how to do proportions with resistors and yeah, proportions with reshaping wires, proportions with resistors and circuits. Like if you have a bunch of resistors in series, how does the voltage? So the current's the same through all of them, right? You should know that. I mean, that should be obvious, right?
Mm-hmm.
But how does the voltage across the resistor relate to? How is it proportional to the resistance? The voltage across the resistor in series. as an example, let's see if you can answer a question like this. Maybe put numbers with it, right? All right. Suppose a 10 ohm, 20 ohm, I'm going to make the numbers easy, and 30 ohm resistor are connected in series, right? I mean, purely in series. If I say in series, I mean purely. I mean, that's implied, right? Okay. Everyone understands that, right? Okay. So, the voltage across the 10 ohm resistor is 5 volts. This is what I'm talking about. So, let's ask, what's the voltage across the other two? All right, does anyone have any answers? So for the 20 ohm resistor, for instance, what's the voltage across it? Yes. What about the 30 ohm? Yes. So there's two different ways to do it. I'll show you both ways because maybe one way is better for someone and the other way is better for someone else. So one way to do it, and I think the easiest way to do it, is that you have Ohm's law, that V is equal to IR, right? The current is the same through all of them. So that means V is proportional to R, directly proportional, because the current's the same, right? So if you double the resistance, the voltage doubles. If you triple the resistance, the voltage triples, right? So the voltage of the resistance of the 20 ohm compared to the 10 ohm is twice as big. So that, therefore, the voltage across it is twice as much. The voltage of the 30 ohm, resistance of the 30 ohm is 3 times bigger than the 10 ohm. So the voltage across it is 3 times bigger. And that's how you do it. I mean, so in other words, V for the 20 ohm is just 2 times V for the 10, right? So it's 2 times 5 volts, which is 10 volts, right? V of the 30 is 3 times the voltage of the 10, which is 3 times 5 volts, which is 15 volts. So the other two are 10 and 15, like you said. The other way to do it is to find the current going through the 10 ohm resistor. All right, so how would you do that? How would you find the current going through the 10 ohm resistor? Right. So the current in the circuit is going to be the voltage across that resistor divided by the 10 ohms, which is half an amp, right? So the current in the circuit is half an amp. And then, yeah, you could do half an amp. So for instance, V10 would be 0.5 amps times, 20, right? We know the 10. Times 20 ohms, which would be 10 volts. And then the 31 would be half an amp, or half of 30, right? Which would be 15. Either way, you get the same answer. But the point is the current's the same. So that means it's proportional to R. You can use the current to find the voltage across the other two resistors. Okay, so let's ask this question. Okay, there's just 2 questions here. What's the power output of the battery? And there's actually 2 ways to answer this question too. But anyhow, what's the power output of the battery? All right, does anyone have the answer first? Yes, that's right. So once again, multiple ways to do this. One way to do it is to find the voltage of the battery first. So how would you find the voltage of the battery? Right. So the voltage of the battery would be 10 volts plus 15 volts plus 5 volts, which would be 30 volts, right? And then you would find the current coming out of the battery by finding the equivalent resistance and dividing the voltage of the battery by the equivalent. Or, you can just find the current through one of the resistors like we already did. We already know it's a half an amp, right? It was what we did in the last part. So the power of the battery is a half of amp times 30 volts, which is 15 watts. So that's 1A and 1B way to do it. There's another way to do it, and that's to find the power dissipated by all the resistors, and then adding them together should be also the voltage, the power from the battery. But just as a check, I'll do it quick. I'm not going to spend a whole lot of time with this way. That's probably the easiest way to do it. Or you could find the power through each resistors, which is just I squared R1 plus I squared R2 plus I squared R3. Anyhow, all you're doing is just squaring the current, which is 1/2, and just adding the resistors together. That's what this simplifies to. So anyhow, what you get is half an amp squared times the equivalent resistance, right? R1 plus R2 plus. So is it 10, 20, and 30?
Yeah.
Which is 60, and a quarter of 60 is 15 watts. So either way, you get the same answer. But let me give you another problem like this with parallel connection, similar to this, and then you can ask me another question if you want. So what if we do the same thing, similar type question, but I'm going to change it a bit, but for parallel. So the same resistors, right? It might not work out to be so nice in parallel, but are connected in parallel. All right. Now, the current through the 10 ohm resistor is, I don't know, let's make it 5 amps, right? So I don't have to change much. All right, same thing, well, not the same question, but similar type question. What's the current through the other 2 resistors? And there's more than one way to do this too, as was the case for part of the last one. Let's see if you can figure it out. Does anyone have the current going through the 20 ohm resistor?
3 amps.
And the current going through the 30 ohm resistor? Yes. So there's 2 ways to do this. One way is to use the fact that, you have Ohm's law for resistors, obviously. But for resistors in parallel, the voltage is the same, correct? So that means that if you want to find the current, which is what I'm asking here, it's V divided by R. So it's inverse related to R, which makes sense. The more resistance you have, the less current you have, right? So if you double the resistance from 10 to 20, that halves the current. And if you triple the current from 10 to 30, that reduces the current by 3, right? So I for the 20 is just, what is it, 6 amps, right? 6 amps divided by 2, because it's twice as big as 10. And then I for the 30 is 6 amps divided by 3, because it's 3 times bigger. So it's 2 amps, right? So it's 6 amps and 2 amps. That's one way to do it. The other way to do it is to find the voltage of the battery. So how would you find the voltage of the battery if you knew the current going through the 10 ohm resistor is 6 amps? Right. Or, right, the voltage of the battery is the current going through any of the resistors times that resistance, right? Because they all have the same voltage. They're in parallel. So it's 6 amps. This is getting really annoying. All right. What is going on here? Okay, so 6 amps times 10 ohms gives you the voltage of the battery. So it's 60 volts. You know the battery in the circuit is 60 volts. So then if you want to find the current, say for the 20 ohm resistor, it's the voltage of the battery divided by 20 ohms, which is 3 amps, right? And then the current for the 30 would be the voltage of the battery, which is 60 volts, because they're in parallel, so it's the same voltage for everything, which is 2 amps, right? So either way gives you the same answer. Okay, now, same question for part B. What's the power output of the battery? Once again, there's more than one way to do it. As long as you know one way to do it, it's fine. All right, does anyone have an answer? No, I just can't say that.
It's 660.
Yes. Okay, so there are two ways to do it. One way is to find the current coming out of the battery. So how would you find the current coming out of the battery?
You just add them up.
Add the
and
voltages
there's-
and that add.
Well, add the currents, right?
Oh,
So there's 11 amps coming out of the battery, right? It's just the sum of the current. And then the power of the battery is always the current going through it times the voltage. So the current coming out of the battery is 11 volts. We know it's 60 volts because we found it in the last part, right? And then you just multiply that together and you get 660 watts, right? So that's one way, and that's fine if you know how to do it that way. The other way, once again, is to find the power distributed by each resistor and just add them together, because that also gives you the power output of the battery. So you could do that too. So actually there's a third way of doing it, but let's just stick with two. So it'd be, V squared over R1. Remember, you use V squared over R for the resistors in parallel. Ugh. All right, so, but this is just V squared times 1 over R1 plus 1 over R2 plus 1 over R3. So this is 60 volts squared times 1 over, was it 10 plus 1 over 20 plus 1 over 30. And that'll give you, if you do it, should give you 660 watts, right? If you do it that way. So either way, you get the same answer. How's it going? All right, so does that make sense? What about capacitors in series and parallel? Well, do you have any questions with that? I mean, so someone wanted to ask me a question.
Oh, that's me.
Great.
Basically, so
Okay.
Stephanie texted me.
Okay.
She said, when you go to the review, can you ask, like he had an example in the homework with the dielectric and the capacitor and disconnecting the capacitor from the battery. If you know what
What this? Okay, we can do.
You're like, that's a lot. That's a lot of words. One second.
No, we can do in the context of multiple capacitors too. Okay, so we can do we can kill multiple birds with one stone. Okay, so all right. So let me think. Okay, so suppose. Okay, suppose I don't know how the numbers work out, but I guess we could do sort of like what we did in the last one. 10 microfarad, right? I think 20 microfarad. Get the same sort of numbers as the last two examples. And 30 microfarad capacitor are connected in series to a battery, obviously, so that they'll be charged. Okay, all right, so the voltage across the 10 microfarad capacitor is, I'm going to make it, I don't know, I'm going to make it 60 volts just to make it something. Okay, so eventually we get to the dielectrics and stuff and disconnecting batteries. Before we do that, what is the voltage across the other two capacitors first? Does anyone have an answer?
No.
Well, okay, so there's two. All right, so what about the 20 microfarad one? Does anyone have an answer for that one? Okay. What about?
That's what
Okay.
he said you have to find out.
So you have 60 and 120 and 30. Okay. What about the 30? Okay, 20. Okay, let's see two different ways of doing it. what is the same for every capacitor connected in series, which is something you should know? The charge is the same.
Oh, never mind. Don't look at this. I knew. We're done.
So Q is CV, so to find the voltage across a specific capacitor is the charge divided by the capacitance.
Yeah.
So V and C are inversely related to one another. So in other words, if you double the capacitance from 10 to 20, that halves the voltage. If you triple the capacitance from 10 to 30, that reduces the voltage by 3. So the voltage across the 20, I always do that, is the voltage across the 10 divided by 2, which is 30 volts. The voltage across the 30, which is 3 times bigger than 10, is the voltage across the 10 divided by 3, which is 20 volts. The other way you can do it is find the charge in the capacitor that you know, which is the 10 one, right? So how much charge is in the 10 microfarad capacitor? It is 60 volts, right, times 10 microfarads.
We're wrong.
So there's 600 microcoulombs, because the microfarad times a volt is a microcoulomb, in that one, but it's also the same in all of them because they're in series. That's the idea in series. So if you know that, you can find the voltage across the 20, remember it's Q over C, right? So it's this charge divided by 20 microfarads, right? The micros cancel out. I'm writing really fast today, and you get 30 volts, right? And the chart and the voltage across the 30 is the same thing, except you're dividing by 30 instead of 20. Either way, you get the same answer of 30 and 20, right? Okay, so related to this, I mean, it's like the other question that I asked. There's multiple ways to do this as well. Actually, I'm going to ask a slightly different question. What's... it's pretty easy to do, though. What's the stored energy in the 20 microfarad and 30 microfarad? So not all three, 2 of them. Capacitor. All right, let's see what. Does anyone have the stored energy in the 20 microfarad capacitor?
9,000.
Yes.
Yes.
What about the?
6,000.
Yes.
I
Okay.
agree.
So there's more than one way to do this, but the way you should do it for this problem, for series, is you use the U is 1/2 Q squared over C. Because the Q is the same for all of them, right? So this is the one you should use. It's like I squared R for series because the current's the same. Here the charge is the same. So for instance, the 20, you would first have to find Q, but we already found Q. So it's 600 microcoulombs squared divided by 20 microfarads. So this gives you 9,000, but the units work out to be, let me show you, you have a micro squared coulomb squared in the top, and then you have microfarad at the bottom. So one of the micros cancel, and you get microcoulomb squared per farad, which is microjoule. So basically, if you keep everything in micro, the units you get out are micro. So it's a microjoule, right? 9,000 microjoules or 9 millijoules, if you want to write it like that. And then it's the same thing for the 30, except you're dividing by 30 instead of 20, right, in the bottom. So you put 30 here, and this is 30, so this is 6,000. It's 2/3 of this, right? So you get 6,000 microjoules and 9,000 microjoules. The other way you could have done it, by the way, because you have any of the equations for stored energy works. So you have 1/2 CV squared, and you know the V because we got it last time. So for instance, for this one, right, you could use 1/2 CV squared, right?
Mhm.
So it's 0.5 times 20, right, times 30 squared. Oops. And you get the same answer, right?
That's what I did.
Yes, and that's fine. But the best equation to use for these series connections of capacitors is Q squared over C times 1/2, right? That's the best one. But I mean, you can get the answer using other equations too. All right, now we're going to get to the dielectrics thing, right? Okay. All right, suppose all these capacitors had no dielectrics originally. Okay, so suppose the 20, I'm just going to pick one of them. It doesn't matter which one. 25 microfarad capacitor is charged, right, to the value that we found in the last two parts. Removed from the circuit. So it's charged and removed. The plates are brought together by, let's say, a factor of, let's do 4, right? So they're 4 times closer together. And a dielectric. What?
Made it sound more difficult when you're laughing.
Am I laughing? It's subconscious laughing. Okay, so in a dielectric, with a dielectric constant
It's inserted.
of 2.5, say, is inserted
What's the capacity?
into the capacitor. Well, that's part of it. That's part of it. So what is the stored energy
Oh.
now? Okay, so try to answer that one, right? So, what's the answer? Yes. Okay, so there's different ways to get this answer as well. So, first thing you got to think about is what happens to the capacitance, right? When you make the plates closer and also you insert a dielectric, right? So if you make the plates closer by a factor of 4, it's the only thing you did. Does anyone know what would happen to the capacitance?
It would increase because they're
Right.
inversely related.
Right, they're inversely related to one another, right? So if you make the plates 4 times closer, the capacitance increases by 4. That's the only thing you did. If you insert a dielectric, what happens to the capacitance? It increases by whatever the dielectric constant is. So you get these two factors that are both increasing the capacitance. The fact that you're inserting a dielectric and making the plates 4 times closer together. So the overall factor is just a product of those two things, right? So the new capacitance is 4 times 2 point, no, sorry. It's 10 times the old capacitance, and we can find that because we know the old capacitance. It's what? 20, right? So it's 200, right, is the new capacitance. If you wanted to find it, you can do it. But we don't even have to do that because for things in, when you disconnect the capacitor, what's the same no matter what you do to the plates? The charge is the same, correct? The charge in the field, right? So that means that if you use this equation again that we just used in the last part, once again, if the charge is the same for a different reason, I mean, in the last part, the charge is the same because they were in series, but this is different. It's the same because it's disconnected from the battery. But nonetheless, it's still the same. It means U and C are inversely related to one another, correct? So if you make the C 10 times bigger, the U is 10 times smaller than originally was, right? So originally the U is 9,000, but now it's 10 times smaller than that, right? Because the capacitance went up by 10. So the U prime now of 20 would be 9,000. divided by 10. And that's it. It's 900. Oh, jeez. Okay, so it's 900 microjoules. I mean, the other way you could do it is actually find the capacitance, which is 200, and then just stick it into the same equation, right? It's just 600 divided by 200 times 2 in the bottom, right? 600 squared divided by 1200, and that gives you 900, right? Either way, you get the same answer. One more part here. One more part. It should be pretty straightforward, and once again, there are 2 different ways of doing it, right? I think there's 2 different ways of doing everything we're doing here. Okay, so what is the voltage across the 20 microfarad capacitor after it has been disconnected? So it's, everything described in part B, right, is what I'm saying. What's the voltage across it, right? After you disconnect it, move the plates closer to one another, and insert the dielectric. That's another way to do it, actually. There's 3 ways to do it.
I see it's 3. For sure, because they also had a movie that was like in I don't even, this was like old. This was posted like weeks ago. Yeah, I picked up on this like at least 2 weeks ago. So I think it's probably a deleted scene.
Now, I'll give you like another minute.
Like this one's also a deleted scene. I don't really know where else. But there's one on where him and Hannah when he brought her to his home. That's the deleted scene. What? Yeah. Oh, and he always cries. In Paradise, he was crying the whole entire season. So ridiculous.
He was crying the whole entire time?
He literally cries in the bathroom.
Oh, yeah.
Paradise is my favorite.
Do you read spoilers or do you just watch the show?
No, I watched it.
You watch it.
See, that was a deleted scene. You never saw that.
No, I didn't see this.
See, that's what I'm saying. Like, they put deleted scenes together and then they make it
Oh,
sound.
yeah, then they put them on YouTube.
No, also they make it seem like something drastic's gonna
Oh,
happen.
yeah, it's not. They just edit it
He's
together.
gonna jump.
Like, the most dramatic episode.
They're like Chris Harrison's like.
Chris Harrison is annoying. I can't stand him. The most dramatic
I
season
think
of
he's
Jackie
so
Ever.
funny. He's so
God.
funny. He's like the moment you've all been waiting for.
Oh, this is.
You can't.
It's a hilarious show.
It's just so funny.
It's really- it's really true.
You actually watch it you're actually like watching it to make fun of them because it's hysterical.
All right, you guys ready? Sorry, I forget to pause the video. All right, does anyone have an answer?
It's 3.
Yes,
Yeah.
it is 3. Okay, so there's different ways to do it. At least 3 different ways of doing it. I'm going to do it what I think is, well, it might not be the simplest, but it's the least amount of math way of doing it. So, what is constant? Once again, if you disconnect the capacitor, move the plates around again, the charge is constant. So if you look at the equation for Q, it's equal to C times V, right? So what do we do to the C from the original capacitance to now? We made it 10 times bigger. right? The U went down by 10, but the C went up by 10, right? It's already right here. So if this goes up by 10, right, what happens to V?
Goes down by 10.
It goes down by 10. That's it. The original V was 30. We found that in part A.
Oh.
If you take 30 divided by 10, that gives you the new V, right? Of course, another way to do it, oh, jeez, is to use the, what am I doing? This thing's annoying me. Is to use the stored energy and then solve for V. You can use 1/2 CV squared, right, with the new C, and then solve for V. What was the third way of doing it? Well, you can either use the other stored energy, 1/2 Q squared C, right, and then, no, that wouldn't do it. No, you can find the Q. The other way to do it is just use this equation with the new C. In other words, you know the new C, it's 10 times bigger than the first C, right? And then you know the Q at 600 microcoulombs, right? So you just solve this equation for V using 600 microcoulombs and the new C, which is 10 times bigger than the first one, right? Anyhow, anyway gives you the same answer if you did everything correctly. All right, so does that make sense? Anything else?
Can you do parenthesis, the V where like you're shaping it out and then change the volume?
Reshaping a wire.
Oh, reshaping a wire. Yeah. Yeah, let's just do one question, right? Like one part to it. It doesn't really have to be that complicated. Where's my thing here? Okay, this is getting annoying. Okay, so, all right, let me think. Okay, so, okay, so a wire is connected to a I'm trying to do the math in my head, so it's a little bit hard to do. All right, so suppose it's connected to a 10-volt battery, and the current in the wire is 90 amps. Don't ask me why I thought of 90, but it's some math I can do in my head. Okay, so then the length of the wire is, it has to be pretty long to have a, resistance you can't ignore. So the length of the wire is, I don't know, let's make it like, okay, so 20 kilometers. Something like that. The wire is melted down and reshaped and connected to the same battery. The current in the wire now is 30 amps. No, sorry, 10 amps. I wanted to be 10. Okay, so the question is, no, I want to make this 30. Sorry, I just thought, make this 30, not 20. Okay, that's fine. The question is, what is the length of the new wire? All right. Does anyone have an answer first before? Yeah.
10.
Almost.
9.5.
Oh. Anyone have an answer? Another answer? Okay, so the first thing you have to figure out is what is going on with the resistance, right? So you have this equation that V is equal to IR for, a wire or any resistor, right? So the voltage is the same. So if you want to find the current, because the current's changing here, it's obviously V divided by R, right? Inversely related to the resistance. So if the current goes from 90 amps to 10 amps, in other words, it goes down by a factor of 9, what has to happen to the resistance of the wire? It goes up by 9, right? So the resistance of the second reshaped wire is 9 times the resistance of the first wire before it was reshaped. So let's write that down so we can keep track of things. Okay, so the new R has to be 9 times the old R. Okay, that's step 1. Now, you have to figure out how do you make the resistance of a wire bigger. So to answer that question, you have to look at this equation for the resistance of a wire. So we're making the wire 9 times bigger, so there's 2 ways to do that, right?
Increase the length or
Increase the area. So what's going on here when you reshape the wire? When you reshape the wire, right, the volume has to be constant, right? Remember this for reshaping wires? So the volume is, area times the length, right? So it gets a little bit weird here, but if you make the length bigger, so the length has to get bigger or the area has to get smaller, right? But this whole thing has to be the same, the area times the length. So if you make the length bigger by some amount, x, this is like the homework problem, right? What happens to the area?
decreases by X.
Right, it would decrease by x. They do opposite things, right? To keep the volume the same, like Play-Doh, when you roll it in your hand, it gets longer and narrower. So if you just made the length of the wire x times bigger, what would happen to the resistance if that's all you did is make the wire 5 times longer or something?
Just increase by
5, right. If you decrease the area by 5, what would happen to the resistance? It would be increasing by 5. Right. So the new resistance, right, is equal to x squared, whatever that factor is, right, times R. But this is equal to 9R because the resistance is 9 times bigger, right? So x is what? 3. And we're making it 3 times longer, not shorter, right? That's, that's how you make the resistance bigger, is by increasing the length and decreasing the area by 3. So we're doing two things. We're making the wire 3 times longer and 3 times more narrow, right? But the question is, what's the length? So the new length is 3 times the old length. So it's 90 kilometers, because if you made it 3 times bigger, that would decrease the area by, 3 times longer. You would decrease the area by 3, which would make it 9 times bigger, which would make the current 9 times smaller, right? Which is what's going on here. All right. Does that make sense?
Opposite.
Right. So if the current went up by 10, it went from 10 to 90, then it would be 3 times smaller. It would be 10 kilometers instead of 30, right? All right. Any other questions? All right, but there's that other review too. That was actually really long. I think that was like 2.5 hours long, that one. But I didn't record the whole thing, so it's like an hour and a half or an hour and 20 minutes or whatever. But it was really long. I remember that one. It was a particularly long review session.